These are the examples for Algebra 2A, Credit 2, Lesson 4.3. Lesson 4.3, we're going to be graphing and solving what we call nonlinear systems. Nonlinear systems means that at least one of our equations, could be both, but at least one of them is not, the graph of that equation will not be a straight line. And looking at the equations, we want to learn how to be able to identify the type of equation it'll be, because that's going to also assist us in graphing. So in our system that we have here, our first equation, y minus 4 equals negative x minus 2 squared, we recognize that as a quadratic equation because the x variable is squared, x minus 2 is squared, but the point is x is being squared. However, the y coordinate or the y part of the equation is not. And so that tells us that's going to be a parabola. And because of the negative in front of the x squared, it's going to be a downward facing parabola. In other words, if there was no negative here, it would be an upward facing parabola. This equation is written in what we call vertex form. The vertex, let's go over vertex form first. Vertex form, y minus k equals a times x minus h squared. The vertex is the hk. And so we can quickly determine the vertex from the equation. But before we do that, notice that there's a minus in front of both the h and the k. And remember, when we see a minus in front of a variable, we're trying to determine a value or an ordered pair out of that, we're going to be taking the opposite sign. So if the vertex is hk, so h, remember, is with the x, that's a negative 2, so that will be a positive 2. And over here, the k is a negative 4, so that will be a positive 4. So remember, when we have minuses, in the general form, we take opposite signs. So the vertex is at 2 and 4, and to plot that point, remember our first value, our x coordinate, and again, that is h and that's k, but plotting a point, that's our x and our y. So we're going to go 2 to the right, because that's a positive 2, and then 4 up, because that's a positive 4. So that's our vertex. Now, you may have graphed a parabola before, and you do this whole table of values, but we're going to show you, hopefully, you might have seen this before, a quicker way of plotting the other points. In any parabola, the points on the other points beside the vertex are going to follow this pattern of 1a, 3a, 5a. So we're not going to have to worry about a, though, because in the examples and the problems you'll be doing, a is either going to be positive 1 or negative 1. So all we have to really do for the problems that we're going to be doing is just determining, to determine whether it's an upward facing parabola or, as we already talked about, in this case, a downward facing parabola. So we won't have to multiply the 1, 3, and 5 by a. So let's go ahead and start plotting the other points. So from the vertex, and let's go ahead and label this for the moment to remind us that this is the vertex. We're going to go left and right 1 unit. And then our first number in our 1, 3, 5 pattern is 1. So we're going to go down 1 unit. And again, it's down, not because it's always down, but again, we already determined that this is a downward facing parabola. Had this negative not been here, it still would be 1 unit, but instead of going down 1, we would have went up 1. All right, so now our next number in our pattern is 3. Again, left and right 1 unit, but this time we're going to go down 3 units. And we end up here. Finally, we're going to go left and right 1 unit, and this last time down 5 units. And so hopefully you see that instead of having, let's careful, 3, 4, 5, instead of having to do a table and do a lot of calculations, we can use that pattern to help us determine the other points. And you can already see the curve there, but of course we're going to connect the points. Whoops, a little off there, huh? And over here, there we go. All right, so that's our parabola. Now our other equation, we recognize that as a linear equation, and the reason we know that is that neither the x and the y is being squared, and more specifically, they have an unwritten exponent of 1. So when that's the case, we know our graph is going to be a line, And since m, the coefficient of x, which remember m is the slope, is negative, we know it's going to be a downward facing line as we go, or downward sloping line as we go from left to right. So, however, though, we're going to start, though, with our y-intercept. Remember, b is our y-intercept. B is 8. So 8 on the y-axis would be up 8 units. And so there's our y-intercept. Now, from that y-intercept, we're going to find other points using the slope. Remember, we want the slope to be a fraction. If it's not, you can make any number or integer a slope by putting it over 1. So from that point, we're going to go down 2, because that's a negative 2. If it had been a positive 2, we'd be going up 2 units. So down 2, and then to the right 1 unit. So down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1. Maybe we'll do one more, down 2, right 1. So now we're going to connect those points, and then all you're going to be doing is after you graph, in your packet, it's a multiple choice. You just choose the graph that matches what you graphed. And let's go ahead and carefully connect those. Okay, that's pretty good. And then also, even though you're not going to be asked to determine the solutions, you can determine the solutions by looking for the points of intersection. And again, all you have to do is match the graph, but just to also focus on that, if we wanted to determine the solutions for this system, we're just looking where the parabola and the line intersect, where the two graphs intersect. So one point was coincidentally here at the vertex, which we already know is 2 and 4. And the other point of intersection is down here. And the coordinates of this point, in other words, how do we get there from the origin? We go 4 to the right, and we're there. There's no up or down, so 4 and 0. So just talking about solutions, but again, all you have to do is just match your graph to the correct graph in the packet. All right, so that is an example for number 1. Now let's take a look at another one, or another example, this one for problem number 2. And let's go ahead and write that up here. So we got an example for number 2. And let's go ahead and take a look at that. So we got y equals x squared plus 6x minus 1, and y equals x minus 1. All right, so now this time, our quadratic equation is not written in vertex form, but what we call standard form, the ax squared plus bx plus c form. You might recognize that or remember that from the quadratic formula. Our linear equation is still written in y equals mx plus b form. We'll talk more about that in a second. Just know if there's no coefficient written for the x, we know that to be a 1, so we can put that in there. But let's start with our focus on the quadratic, graphing the parabola. And again, we know it's a parabola because x is squared, y is not. And this time, though, x squared doesn't have a negative here, so we know it's a positive. So this is going to be an upward-facing parabola. Now, you might wonder, well, okay, so if it's not written in vertex form and it's written in standard form, how do we determine the vertex? Well, there's 2 ways we can do that. We can manipulate the equation around to put it into vertex form, or we can use a small little formula, and you're going to see that right now, to assist us in determining the vertex. And what it'll do is give us the x coordinate of the vertex, and then we'll use that to find the y coordinate. So that little formula is just negative b over 2a, and yes, that's the same a and b from the quadratic formula. Notice there's no c here, so even though we do have a c value, we're not concerned with that. A is the coefficient of x squared, so a is 1. B is the coefficient of x, so b is a positive 6. Positive 1, positive 6. And now we're going to substitute them into our formula here. So we have negative b, so a negative positive 6, which ends up just being negative 6, and over 2 times a, remember a is 1, 2 times 1 is 2, negative 6 divided by 2 is negative 3. So the x coordinate of the vertex is negative 3. To find the y coordinate, we're going to take that -3 and substitute it in for x. So we have y equals -3 squared plus 6 times -3 minus 1. And so we're going to simplify this using our order of operations, which means exponents, then multiply, and then add or subtract. So -3 squared, which means -3 times -3 is a positive 9. 6 or positive 6 times -3 is -18, and then minus 1. Now, to do our subtraction, of course, you can use a calculator, but also you can try and think this through. So let's go over the rules quickly. We have a positive and a negative, so we're going to subtract 18 minus 9 is 9. However, the larger number is negative, so -9. Now, -9 and -1, the signs are the same, so we're going to add them. That's 10. Both numbers are negative, so -10. So y is -10. So our vertex is going to be at -3, -10. So let's go ahead and plot that point. And again, we are going through this at full speed. So if you need to, if you're like, wait a second, what did you do there? Let's draw a line between these two to separate that. Remember, pause, rewind the video as needed to just make sure you have a good understanding of what's going on. So plotting this vertex at -3, -10, let's identify that as the vertex. So -3 would be 3 to the left. Remember, our first number in our ordered pairs, left or right. So it's negative, we go to the left. And then -10 for the y coordinate. So we're going to go down, carefully counting this, 10 units. So there's our vertex at -3, -10. All right, so now we're going to use our 1, 3, 5 pattern, but this time we have an upward facing parabola. So as we go left and right 1 unit, we're going to go up 1 unit to begin. Then left and right 1 unit again, and this time we'll go up 3 units. And then finally left and right from this point, our most current point. And then now for the last set of points, we're going to go up 5 units. So 2, 4, 5, and 2, 4, 5. So again, you can already kind of see the curve there with the points, but of course we're going to connect that. Let's get rid of that. And so we're going to connect the points. And we've got our parabola. All right, so now we need to graph the linear equation. So we always start with our y-intercept, which is -1. Our slope is +1, but we need it as a fraction, so we're going to put it over 1. So from this point, from the y-intercept, remember slope again is rise over run. So from this y-intercept, we're going to go up 1 because it's a +1 this time, and then to the right 1 unit. So up 1, right 1, up 1, right 1. You might ask, well, how many points do you need to do? Well, if you're drawing a line, you only need 2 points, but you want it as accurate as possible. So we're doing, several, and it's quick. Up 1, right 1, up 1, right 1. That's probably enough. And now we're going to connect those points. And once again, once we do that, we'll match that to the correct graph. And we'll also talk, even if we're not asked for it, we're going to talk about the solutions as well. So we have our graph. Again, if this was the actual problem, you would just match that to the correct graph in your packet and circle the correct choice. And again, just to identify the solutions, even though we're not asked for them, we have one solution right here. Now, what are the coordinates of this point? We don't go left or right at all from the origin, just down 1. So that would be 0, -1, because there was 0 because there was nothing left or right. And this point down here, we go 5 to the left and then 3, 6 down. So 5 to the left is -5 and 6 down is -6. So if we were asked for the solutions, those would be the solutions to the system. Just one last point on that. Remember, every point on the line is a solution to the linear equation, and every point on the parabola is a solution to the quadratic equation. It's only at the points of intersection that those are the solutions to both equations. All right, so that's it for our example for number 2. Problems 3 and 4, we're going to verify or determine solutions to a quadratic equation given a set of points, and we're going to determine which ones are solutions to the quadratic equation by substituting those points in. So let's go ahead and take our graph off there. And let's take a look at our first example. So this example will more closely tie to number 3. It's kind of the same thing on both 3 and 4, but we're going to look at a separate example for both of those. All right, so our first equation, for the example for number 3 is y equals x plus 2, and the other equation is y equals x squared plus 2. All right, the first ordered pair that we're going to be checking is 0 and 2. Now remember, as we said, in order for, when we looked at the graph, the only solutions were the points of intersection on the graph. In other words, an ordered pair that is a solution to both equations. So if we're going to be doing this algebraically, in order for an ordered pair to be a solution, it must make both equations true. And we'll talk about what that means in a second. So our first ordered pair is 0, 2. And remember, your first number in any ordered pair is your x. The second is your y. So y, looking at our first equation, y is 2. X is 0. 0 plus 2 is 2. 2 equals 2. That is a true statement. So 0, 2 is a solution to the first equation. But we have not determined yet whether it's a solution to the system. We need to see if it also works in our other equation. So once again, 2 substituted for y, 0 for x, 0 squared, which means 0 times 0 is 0. And then 0 plus 2 is 2. And again, that's a true statement. And true statement just means we have the same number on both sides of the equal sign. If the numbers are different, like 2 and 5 or 2 and negative 2, then that would be a false statement. But as it is, 0, 2 is a solution to the first equation and the second. So 0, 2 would be our first solution. So let's go ahead and put that up here. So 0, 2 is our first solution. Now, the next ordered pair that we're going to check is 1 and 3. And let's go ahead and try that one. So 1 and 3. So again, x is 1, y is 3. So we're going to substitute 3 in for y, 1 in for x. 1 plus 2 is 3. We have 3 equals 3. That is a true statement. So 1, 3 is a solution to the first equation. Now let's see if it's a solution to our second equation. Y is 3. X is 1. 1 squared. Now careful, a common error with this is people will think 1 times 2, but remember that's not what you're doing. 1 squared means 1 times itself. In other words, 1 times 1, which is 1. And then 1 plus 2, of course, is 3. And that's a true statement. So because 3, we have the same number on both sides of the equal sign, 3 equals 3. So 1, 3 is a solution to the first equation. It's a solution to the second equation. And so that would be a solution to our system, 1, 3. Now, we're given another ordered pair. But let's think about this for a second. The last one's 4 and 2. Now, we don't even need to check this point. Why is that? Here's why. So the first equation, neither x nor y is being squared. So we know that's a linear equation and it's a positive slope. So it's going to look something like that. The other equation over here is a quadratic because x is squared, y is not. So we're going to have, and that's a positive x squared. So we're going to have a positive or upward facing parabola. When your nonlinear system includes a line and a parabola, the most number of solutions that you can have is 2. And because there's no way for that line to intersect the parabola in more than 2 points. Now, it could be less than 2. It could be 1 where the line just touches the parabola, or it could even be none where the line doesn't intersect the parabola at all. So you can have 2 solutions, 1 solution, or no solutions. But the point is here is the most you can have is 2 solutions. You might think, well, what if we bend that line somehow? You could, you could, but again, that's no longer a linear equation. So that wouldn't apply here. So since the most number of solutions you have is 2, and we already found 2 solutions, then that means we are done. We don't need to check the last ordered pair because we found our 2 solutions. And so we would, and I believe you're answering yes or no in your packet. So you would answer yes to the first one, yes to the second, had this been the actual problem, and then no to the third by default. Now, if you want to, you can check it to be sure, but we've checked here pretty good, so we know that we found our two solutions and we're good to go. All right, so now let's take a look at an example for number 4. For number 4, we have these two equations. And again, it's the same process. We have x minus y equals 2, and we have y squared minus 20 equals negative x squared. Make sure we can see that okay. I think so. All right, so now this time we have let's think about the type of equations we're going to be working with here. X and y both have an unwritten exponent of 1, so that's a line. Now here, both x and y are being squared. Now, if that's the case, there's two possibilities. It could be a circle or an ellipse. We're not working with ellipses right now, so I'll tell you it is a circle. So the most number of points of intersection with a line and a circle would once again be 2. And so we could have at the most 2 solutions. But again, if the line could just touch the circle, 1 solution, or not intersected at all, which in that case would be no solution. So 2 solutions, 1 solution, or no solutions. All right, let's go ahead and check our first ordered pair. Our first ordered pair, interestingly, is 4 and 2. So let's see if 4 and 2 works in this system. Remember, in any ordered pair, x is first, y is second. So x is 4 minus y, which is 2. 4 minus 2 is 2. We have the same number on both sides of the equal sign, so that is a true statement. So 4, 2 is a solution to the first equation. Now, in our second equation, we have y is 2, so we have 2 squared minus 20 equals negative x squared, and x is 4. Now, notice there's a negative in front of the x squared, so we're going to square whatever x is and then make that answer negative. So the negative was already there. It's not part of what's being squared. So 2 squared, 2 times 2 is 4. And then 4 minus 20 is negative 16. Remember, signs are different. So we subtract 20 minus 4 is 16. Larger number is negative, so negative 16. Over here, we have 4 squared, which is 4 times 4, which is 16. But we have the negative in front, which is bringing it all the way down here, which makes it negative 16. We have the same number on both sides of the equal sign. So it turns out 4, 2 is a solution to our system, to this system. I know a minute ago we talked it wasn't a solution to the last system, but it is to this one. All right, so let's check our next ordered pair here. Our next ordered pair is 2, negative 3. X is 2, y is negative 3. So we have 2 minus a negative 3. So we have 2 negatives there, a negative from the subtraction and a negative from the fact that y is negative 3. Remember, a negative negative becomes a positive. So we have 2 plus 3, which is 5. And here we don't have the same number. This is not a true statement. We don't have the same number on both sides of the equal sign. That is a false statement. And so we know that 2, negative 3 is not a solution to our first equation. If it's not a solution to your first equation, you don't even need to bother with the second. You say, well, yeah, but what if it's a solution to the second? At this point, it doesn't matter because remember, in order to be a solution to the system, it has to work in both equations. So if it doesn't work in the first, no reason to even bother with the second. So 4, 2 was a solution, so we would answer yes to that. But 2, negative 3 is not a solution, so we would answer no to that one. All right, we've got one more to see if we can find another solution, one more ordered pair, and that's negative 2, negative 4. So again, negative 2 is our x, negative 4 is our y. So we have negative 2 minus a negative 4. And again, we have that negative negative, which becomes a positive. Negative 2 plus 4 is positive 2 because the signs are different. We subtract 4 minus 2 is 2. The larger number is positive, so positive 2. So since we have the same number on both sides of the equal sign, that is a true statement, and -2, -4 is a solution to the first equation. But is it a solution to the second equation? Well, let's see. We substitute -4 in for y, so we have -4 squared minus 20 equals -x squared, and x is a -2. All right, so let's go ahead and work out the left side here. Now, in this case, the negative is being squared because the value of y was a -4. So -4 squared means -4 times -4, which is a positive 16. 4 times 4 is 16. A negative times a negative is a positive. And then 16 minus 20 is -4. The signs are different, so we subtract. We get 4. Larger numbers negative, so -4. Here we have -2 squared, which means -2 times -2, which is a positive 4. And you might look and say, well, wait, okay, those numbers are different, so it's not a solution. But hold on. Remember, we have that negative in front of the whole thing, which makes it a -4. It's the same number on both sides of the equal sign. That's a true statement. So the last ordered pair, -2, -4, we would answer yes to. And so -2, -4 is our other solution. So again, if this had been an actual problem in your packet, remember you check yes for the ones that are true, and then make sure you check no to the ones that are not true, that are not solutions. Sometimes that happens where we're just looking for the ones that are the solutions. We check yes to those, but we leave the other one blank. And so make sure you do that. Otherwise, that'll get it marked wrong if you don't check no to the one that's no. All right, so that is it for example for number 4. For number 5, the last problem, and again, I know we got a lot going on here, but this is it. So for that, we're actually going to, it's a word problem that we're actually going to do on Desmos. And so let's go ahead and share the screen for Desmos. And let's go, and then we'll read the problem here. All right, so here we go. For number 5, it says, and again, we'll read the problem and then we'll substitute in our the equations we'll use for the example. It says the flight of a cannonball, this is on page 51, by the way, number 5. The flight of a cannonball toward a hill is described by the parabola y equals 2 plus 0.12x minus 0.002x squared, where x is time in terms of seconds and y is the distance in terms of miles. The hill slopes upward along a path given by y equals 0.15x. Where on the hill does the cannonball land? All right. So what's nice about this is that Desmos will do the work for us. So now the equation that we're going to use is this. We have y equals 3. Oh, can't see because of the glare. There we go. 3 plus 0.24x minus 0.003x squared. Now, the easiest way to get into the exponent, don't just type a 2 because that'll give you a subscript. Pressing Shift and 6 will take you into the exponent and just type your 2 and type the 2 there. Another way to do that is to bring up the keyboard and then just type, you see where it says a squared there, just type that. Maybe that sounds a little bit easier. The other equation is going to be y equals 0.15x. So we're going to be using the same equation for that one. And so that's the slope of the hill is going to be the same. It's just the height of the cannonball is going to have a different equation. So you want to enter those two equations into Desmos. And what you're looking for is where, let's go ahead and zoom out so we can see that. And so the height of the path of the cannonball is the parabola, the curve there. So I know this sounds, I know there's a lot of cannonballs out there today, but anyways, we'll go with what we have here. So this is the path of the cannonball, and then the line represents the slope of the hill. So what we're looking for is where that cannonball lies on the hill. And so what you're going to do is you can zoom in if you want, don't really need to. Click either the parabola or the line. Either one will give us this gray dot here. And we just hover over that and we get our solution. And so in our example, it's the ordered pair is 50 and 7.5. So what does that mean? Well, remember they said that the x value represents the time in seconds, I believe, right? Yeah, x represents the time in terms of seconds, and y is the y coordinate is the distance in miles. So interpreting the answer in context, we don't want to just write an ordered pair in our packet. We would write after 50 seconds, the cannonball lands 7.5 miles up the hill. So again, because x was our time in seconds, so after 50 seconds, the cannonball lands, make sure we get all that right, 7.5 miles, because y is the distance in terms of miles, 7.5 miles up the hill. All right, so that's it for lesson 4.3. Again, if you have, let's go ahead and, well, we'll just leave that there. If you have any questions, or you know, the video, it's you got trying to get a better understanding. Remember, pause, rewind the video, and again, to as much as needed. And good luck with the work. And we'll see you in the next video. Take care and God bless.